So let's start with our digital electronics class. Till date, we have covered combinational logic design. So far, we covered the concepts on number system, Boolean algebra, algebraic and kernel map optimization, the detailed steps of combinational designing process. So from today's lecture, we'll start sequential logic circuit. So what is sequential logic circuits? Sequential logic circuits have the property that the output depends not only on the present input but also on the past output. In order to understand sequential logic circuits, let us recall the basic block diagram of combinational logic circuit. This is the basic block diagram of combinational logic circuit. You can see in the left side we have sets of inputs, in the right side we have sets of outputs. Now this output depends on the present inputs only. Whenever the inputs are available, then outputs will also be available. If there is no input, the output will not be there. And this output doesn't depend on the past inputs or other feedbacks. It only depends on the present input. But unlike combinational logic circuit, the sequential logic circuit has different properties. Suppose we will design a switch uh, that will operate a light, simple light. Okay, so the same push button switch will be used for switching on and switching off the light. So if I press the push button, the lights will be on if the present condition or present state of the light is off. Again, same push button will switch off the light if the present condition or present state of the light is off. So in this case, we need to know what is the condition of the present output. So we'll take an output or a feedback from the output panel. Even though we are giving the same input, that means a pulse, but the output will be different based on the present output condition. So next output will be different based on the present output condition. If the present output condition is on, then pressing the same switch will switch off the light. So we need to take a feedback from the output side. Another example, suppose we want to design a counter. So if I give input that based on that input, it will count the next number. Suppose so if, in the counter, if we have the present condition is 4, so the next value will be 5 for the same input. If the present condition is 6, the next value will be 7. So we need to have a feedback from the output side to know what is my present condition, and based on that previous output, the next output will be decided for the same inputs. So let me show you the block diagram for sequential logic circuit. So this is the basic block diagram of combinational logic that we learned from our previous figure that is drawn in the left side. Okay, I have given all the inputs in the left side, all the inputs together. This is the set of inputs and set of outputs. Now the example that I gave you earlier, that I told you that if the present condition of my output, suppose the light example, the present condition of the light is on. If the present condition of the light is on, so if I give the input here, if I provide the same input here, the light will be off. So the next state will be of the light will be off. Now off. But if the present condition of this light is off, pressing the same switch will make the light on. So to know the present condition of this circuit, we need to have a feedback from this output side, from from this output panel. That's why a feedback is taken, and that feedback is kept in a memory unit. This is the memory or storage element. That feedback will be stored in this memory unit. Now this memory unit will act as input uh, to decide the next output, even though I am giving this or I am providing the pulse from the same input switch. So this input switch and the present state, which has been taken from the memory unit and that was stored from the output panel, will decide together they will decide what will be the next output. So output, in this case we can see that output depends not only on present input but also on the past output. This output, can see, this output depends not only on the present input, this is the present input, but also the past output that was stored in this memory element. So combinedly complete block this complete block combinedly I can say this complete box combinedly known as sequential logic circuit. In the previous slide, we have seen one of the basic features, or one of the main features of sequential logic circuit is the memory unit. Here we'll know how to design the basic memory unit of the sequential logic circuit. The basic storage element or memory element is called latch. So at the very beginning, we'll design a latch. There are different types of latch, which I'm going to describe in my next slides. But we'll start with the basic latch, that is basic SR latch. SR stands for set and reset, set and reset. So we'll design our SR latch using NOR gate. Let me tell you the function of NOR gate. So we know in a NOR gate, if one of the input of NOR gate is 1, if one of the new input of the NOR gate is 1, we do not care about other input. So the definite output will be 0. It's for sure. So if we know the one of the input is 1, the output will be 0 for NOR gate case. On the other hand, if we know that one of the input of the NOR gate is 0, we cannot say what is the definite output unless or until we know the second input. If the second input is 0, the output will be 1. If the second input is 1, the output will be 0. But as I said in the previous case, that if one of the input is 1, if one of the input is 1, we do not care about this input, either it is 0 or 1, the output is definitely 0. So this phenomenon will be used for designing the basic SR latch. The basic SR latch will be designed using two NOR gate. One of the feedbacks will be taken from the first NOR gate and output of the first NOR gate to the input of the second NOR gate, like this way. And another feedback will be taken from the second output of the second NOR gate to the input of the first NOR gate. So let's name the inputs. This is set input. In digital electronics, set means making the output 1. So whenever this output equal to set, that means set means I'm giving this output equal to 1. I'm setting the circuit. This is the reset input in digital electronics. When we say resetting the output or reset the output, that means I'm making the output 0. So if this input is equal to 1, that means I'm making or I'm resetting the outputs. This is my Q output of this latch, and this is Q prime. So these two outputs, this is my original output Q. So if this Q equal to 0, definitely Q prime will be 1. If Q equal to 1, Q prime will be 0. So they are complement of each other. So this is the main output, and this is the complemented output. Let's describe the operation of SR latch. At the very beginning, if we take S equal to 0 and R equal to 0, as I told you earlier, that if one of the input of NOR gate, if one of the input of NOR gate is 0, unless and until I know the second input, I cannot predict what is my current output. So for this NOR gate, I do not know what will be the output unless or until I know the I know another input. And for this NOR gate as well, if I do not know what is my another input, I cannot predict what is what will be my next output. So this second input has been taken from the output of opposite NOR gate. So in order to mitigate this problem, instead of taking s equal to 0, r equal to 0 at the very beginning, we will take s equal to 1, r equal to 0 to predict our output. So here I am taking s equal to 1, the first case, and r equal to 0. If s equal to 1, that means one of the input of the first uh, NOR gate, this is the first NOR gate, if I consider this the first NOR gate, if one of the input of this NOR gate is 1, so I can say I do not care about this input, the output here will be definitely 0. So as one of the input of the NOR gate is 1, output of this NOR gate will be 0. This 0 will appear as the second input here is 0. So as I have already taken r equal to 0 and this input is also 0, so this 0 0 will combinedly give me the output equal to 1. So I am getting this output 1 here. This one output will be available in the input side of the first NOR gate, that is the downward, in the downward. So this one and this one will again give me the 0 output, and this 0 will appear here, and this 0 0 will give me the 1 output, and this 1 and 0 is the stable output. So for s equal to 1 and r equal to 0, I am getting q equal to 1 and q bar equal to, or q prime equal to 0. So and this is the stable output. So if I draw this in function table, this is the function table. At the very beginning, the value of s is taken as s equal to 1 and r equal to 0, and we have got the value of q equal to 1 and q prime equal to 0. Now we know the previous value, that means present value of q equal to 1 and the present value of q prime is 0. After giving this 1 and 0, next we'll give s equal to 0 and r equal to 0. From the previous case, we know our previous value of q was 1 and previous value of q prime was 0. So this 1 will appear from here to, as the input of the of this NOR gate. So 1 will be appearing here, and we have given 0 here. So 0 1 will give me the output 0, as one of the input of NOR gate is 1, so that will give me the output 0. This 0 will appear here, so this 0 and r equal to 0, so both 0 0 will give me the 1. So this 1 again will appear here, and it will give me the output 0. This 0 will appear here, and r equal to 0, so this 0 0 will give me the value of q equal to 1. So in this case as well, for 0 0 input, we can see s equal to 0 and r equal to 0 input, we can see the output q equal to 1 and q prime equal to 0, and this is the stable output. This is stable output. This is also stable output. So we can say for s equal to 0, r equal to 0, the output q equal to 1 and q prime equal to 0. Next, let's consider s equal to 0 and r equal to 1. So as r equal to 1, so one of the input of the upper NOR gate, this NOR gate is 1. We can say the definite output of this NOR gate is 0. So we do not care about the input of the second input of the upper NOR gate. As one of the input of this NOR gate is 1, the definite output will be 0. This 0 will appear at the input side of the lower NOR gate. This 0 will appear at the input side of the lower NOR gate. Now here we'll have 0 and s equal to 0, another input is 0. This both 0 will give me output 1 here. So this 1 will be appearing at the second input of the upper NOR gate. So in upper NOR gate we have 1 1. Eventually this 1 1 will give me 0 here, and this 0 will appear at the lower NOR gate, input of the lower NOR gate, and the 0 0 will give me 1 here. So this 1 and 0, that means q equal to 0 and q prime equal to 1, they are stable output. So we can say for s equal to 0 and r equal to 1, the output that we are getting, q equal to 0, q prime equal to 1. Next, considering this state as my present state, that means the value of q is equal to 0 and the value of q prime is equal to 1. Again, I'm going to give s equal to 0, r equal to 0. That means I'm changing the input values, s equal to 0, r equal to 0. Let's see what happens. For s equal to 0 and r equal to 0, one of the inputs of the NOR gate is 0. Unless I know the input, another input of the NOR gate, we cannot predict the output. So let's start with q. Q is equal to 0. This q is equal to 0. This 0 will appear at the input side of the lower NOR gate. So here we'll get 0. Both zeros, this 0 and this 0, will give me an output q prime equal to 1. So we see 1 remains unchanged. Q prime, the value of q prime remains unchanged. This 1 will appear at the second input of the upper NOR gate. So here this 1 will appear. 1 and 0. 1 and 0 will give me an output q equal to 0. So q equal to 0 also, it doesn't change. So this 0 again, it will appear here, 0 0. This 0 and 0 will give me the value equal to 1, q prime equal to 1. This 1 will appear here, this 1 0 will give us a value q equal to 0. So we can say these outputs are stable outputs. So for s equal to 0, r equal to 0, we are getting uh, a set of output where q equal to 0 and q prime equal to 1. Here we can see a very interesting feature. So what is that interesting feature? We can see for s equal to 0 and r equal to 0, we are getting q equal to 1 and q prime equal to 0. For the same set of s inputs, that means s equal to 0 and r equal to 0, we are getting q equal to 0, q prime equal to 1, two opposite results. So here we have one result, here another result. So what does it signify? Whenever we have previous state q equal to 1, after having this previous state, if we provide 0 0 input, it holds the previous data. Q, if q equal to 1, after giving 0 0 input, the value of q remains 1. If we have previous value q equal to 0, and after that if we provide this input q equal to s equal to 0 and r equal to 0, we get the same result and the output side, that means 0 remains 0. We can conclude that the 0 0 input for s equal to 0 and r equal to 0, it gives an output where it holds the previous output. If the previous value of q is equal to 1, after giving 0 0 input, it will remain 1. If the previous value of q is 0, after giving 0 0 input, it will remain 0. Next, let's see what happens if we provide s equal to 1 and r equal to 1. Till now, we have seen all the possible combinations except s equal to 1 and r equal to 1. If we give s equal to 1 and r equal to 1, that means one of the input of the NOR gates, this NOR gates is 1. So if I take the lower NOR gate first, one of the input of this NOR gate is 1, that means the definite output q prime is equal to 0. So if this q prime value is 0, this 0 will appear here, and another input is 1. I don't care about this input. Again, q will be equal to 0. We can see for input s equal to 1 and r equal to 1, we are getting q equal to 0 and q prime also equal to 0. So this is an invalid condition because it violates the requirement that the outputs be the complements of each other. So for Sr Latch, the inputs s equal to 1 and r equal to 1, these inputs are called invalid input because we are getting q equal to 0 and q prime equal to 0. It also results in an indeterminate or predictable next state when both inputs are 0 after this state. For example, now if we consider this is my present state, q equal to 0 and q prime equal to 0. Now I am giving, let me take another color. Now I am giving s equal to 0 and r equal to 0 after this step. Whenever I am providing s equal to 0, let's start with the lower, no, lower NOR gate first. We have s equal to 0, and I'm getting another 0 from this q output. This 0 and 0, this 0 and 0 will return q prime equal to 1. Fine. This 1 will appear here, and this 1 and 0 will return me 0 here. This 1 and 1 and 0 will return me 0 here. Fine. What if I have started with the lower one. What if I start with the upper one? Suppose the present state was q equal to 0 and q prime equal to 0. Now I am giving 0 0 input, 0 0 input, here 0 and here 0. S equal to 0, r equal to 0. Now let's start with this upper one. The upper one, one of the input is 0, another input will come from q prime. So this q prime 0 will appear here. So here we have 0 and 0. Both the inputs are 0. What will be the output? The output will be 1. Output will be 1. This one will appear here. This one will appear here. So here we have 0 in one input. This input is 0, and another input will be 1 because this 1 is appearing here. So this is 1. This 1 0 will make the output 0. So we can see for the same set of input, that means 0 0 0 0 input. If I start from the lower one, I am getting this 0 and 1 output. Again, for same set of input, 0 0 input, if I start from the upper one, we are getting 1 0 output. That means this is not predictable output. This is unpredictable next state when both inputs return to 0 simultaneously. That's why, considering all this case, whenever we have s equal to 1 and r equal to 1, the output, or we can say these states, is an invalid state. We can see the graphical symbol for Sr Latch. Inside this box, we have this logic diagram. So the inputs are S and R, and the outputs are Q and Q prime. In a nutshell, we can say when the value of S equal to 1, that means I am making the circuit output set, or I am setting the circuit output. Setting the circuit output or latch output means Q equal to 1. So when S equal to 1, provided R equal to 0, S equal to 1, that means setting the latch, output will be 1. When R equal to 1, that means I am resetting the latch, the output, resetting means output of that latch will be 0, provided other input is 0. So when S equal to 1, that means setting the latch, the output will be 1. When reset equal to 1, that means resetting the latch, output will be 0. So setting means 1, resetting means 0. If I have input S equal to 0 and R equal to 0, S equal to 0 and R equal to 0, the output will be the previous output of Q. That means it will hold the previous value of Q. If the previous value of Q is 1, then the next value of Q will be 1. Again, for same 0 0 input, if the previous value of Q is 0, then the next value of Q will also be 0. So the 0 0 input will hold the previous value of Q. It will act as memory. That means it's holding 1 bit data. For 1 1 input, as I told you earlier, the 1 1 input will be considered as invalid input. Here, the same Sr latch is designed using two NAND gates. Unlike the previous case, the NAND gate has a unique feature that if one of the input of NAND gate is 0, the definite output of the NAND gate is 1. We do not care about other input. So whenever one of the input of NAND gate is 0, the input will be output will be 1. Definite output will be 1. Utilizing these characteristics, we can explain the operation principle of this Sr latch as I explained the previous case. Here, to have the similarity with the previous case 1, the set is defined by S prime and reset is defined by R prime. That means these are active low. So when S prime equal to 0, what does it mean? S equal to 1. R prime equal to 1, it means R equal to 0. That means this is the set condition. When we have the set condition, the output is set. Output Q equal to 1. When S prime equal to 1 and R prime equal to 1, that means S equal to 0, R equal to 0, this will hold the previous data. This is holding the previous data. Previous value of Q was 1. Next, after giving S prime equal to 1 and R prime equal to 1, I'm getting the same value of Q. That means it's holding the previous data. When R prime equal to 0, R prime equal to 0 means R equal to 1 and S prime equal to 1 means S equal to 0. This is the reset condition. So output will be uh, output will give us the reset value. Reset value means 0 value. Again, after having this condition, if I give S prime equal to 1 and R prime equal to 1, what does it mean? I am giving S equal to 0, R equal to 0, it will hold the previous data. What was the previous data? Previous data was 0 and P0 will be kept in the memory. So it's acting like a memory. And for 0, 0 input, for the value of S prime is 0, R prime is 0, means S equal to 1, R equal to 1. I want to have the similarity with the previous case, then this is the invalid output. From the previous slide, it is clear that the output of any latch depends on the input of the latch. That means when S equal to 1, output will be set. When R equal to 1, output will be reset. When S equal to 0 and R equal to 0, output it will hold the previous data. However, the operation of the basic NOR and NAND latches can be modified by providing an additional control input. An additional control input that determines when the state of the latch can be changed. How is it done? It is done by adding two extra NAND gate. You can see we have added two extra NAND gate, and one of the inputs of these NAND gates are commonly connected, and this is supplied by a common signal, that is C. What is C? C is named as control signal. I repeat, C is named as control signal. Now, when C is equal to 0, C is equal to 0, we do not care about the value of S and R, as one of the input of this NAND gate, and this NAND gate is 0. The value that will be available here is 1, and the value that will be available here is 1. From the previous slide, we know that whenever we have 1 signal, the output Q will hold the previous output. That means there will be no change in the output side. Even though I am changing the value of S and R, but it won't change the output value because control signal is equal to 0. That means control signal is controlling the input when it is to be transmitted. However, if the control signal, the value of the control signal is equal to 1, that means this P and Q value depends on the value of S and R. Suppose S equal to 1. We are giving S equal to 1 after giving control signal equal to 1. So S equal to 1 will give us P value equal to 0, r equal to 0 will give us q value equal to 1. That means I'm giving s equal to 1 means set r equal to 0. S equal to 1 means set. So whenever we have P0 and Q1 from our previous operation of SR latch using NAND gates, we know for this was equivalent to S prime value. This was S prime and this was R prime. The value of S prime is 0, the value of R prime is 1. It means that the output will be set. Output will be set. So we can see this will act as our normal latch it will act like our normal latch case if the control signal is equal to 1. If the control signal equal to 0, then the output will hold the previous data. There will be no change. If the control signal is equal to 1, whatever data we have here, they are allowed to pass from this side to that side and this side to that side, and the latch will operate accordingly. So the control signal is controlling the input signal when it is to be transmitted. So if we see the function table, this is the function table. If the control signal value is equal to 0, we don't care about S and R value. The next state of Q will be the previous value. That means there will be no change. If control signal is equal to 1, for S equal to 0, R equal to 0, it will hold the previous data. That means no change. If control signal is 1, then S equal to 1, R equal to 0, that means the circuit will be set, latch will set. If control signal value is 1 and S equal to 0, R equal to 1, R equal to 1 means it's reset, and 1 1 invalid case, uh, like previous case. So this control signal is playing a vital role for this type of latch. So this type of latch is named as SR latch with control input. SR latch with control input. Let's see a timeline diagram that will clarify your idea. Let's draw the timeline diagram uh, for this latch. We have control signal here. We have S input and R input. We need to draw the output Q. So at the very initial moment, we see uh, control signal for this portion. Let's draw this part. For this portion, control signal equal to 1. So whenever we have control signal is equal to 1, that means the output will act based on the input signal. Control signal 1 means it will act based on the input signal. In input signal side, we have S equal to 1 here, R equal to 0. So whenever the value of S is equal to 1, so what will be the value of Q? Q will be set. Q will be set. Up to this much, Q will be set. Fine. Here in the next side, control signal equal to 1. So up to this value, control signal is 1, but S equal to 0, R equal to 0. As S equal to 0, R equal to 0, it will hold the previous data. The previous data is 1, so it will continue the value 1. Now from here to here, we do not care about the input S and R, because for this portion the control value of control signal is 0. Value of control signal is 0. When we have C equal to 0, we do not care about, or we do not care about the value of S and R. It will hold the previous data. So it will hold the previous data up to this much. Now after this line, again the control signal becomes 1. Here the value of control signal is 1. When we have control signal equal to 1, now let's see this portion. We have S equal to 0, R equal to 1. When we have S equal to 0 and R equal to 1, the circuit is the output of the circuit, output of the SR latch will be reset. So reset means 0. So it will go from set value to reset value, and it will continue up to this much. Now here again we have control signal 1, but it's 0. This is also 0. So for 0 0 input, it will hold the previous data. Now here again, control signal 0, we do not care about the inputs, it will hold the previous data. Now for this portion, control signal is 1, this is 0, and this is 0 0 0, SR0 S0 R0, so it will hold the previous data. Here control signal 1, for this small portion, control signal is equal to 1. You can say this portion, control signal is equal to 1. Let's draw 1 here. 1, set 1, reset 0, set 1, reset 0. So the circuit will go in set mode. Now for this portion, from here to here, this portion again control signal 0. We do not care about the inputs. Whenever we have control signal is equal to 0, it will hold the previous data. What is the previous data? Previous data was 1, so it will 1 will continue. Again here control signal is equal to 1 and it's set, so circuit will be set up to this much. Again let's draw this portion. In this portion, control signal 1, S is 0 and R0, so it will hold the previous data. Is 0 R0, it will hold the previous data. Again control signal 1 is 0 R1, the circuit will go to the reset value, so it will come down. This is, so ultimately this will be the Q output for this timeline diagram. I think all of you understood. This is a typical SR latch with control input. You can see the control input. Whenever this control input, this control signal is supplied by clock pulse, that means CP, clock pulse or clock pulse train, then this type of latch with control input that is supplied by clock pulse is renamed as flip-flop. Before I start flip-flop, let me give you a brief idea on clock pulse. What is clock pulse? This is a typical timing diagram of clock pulse or clock pulse train. It's a continuous signal, and we can see it's producing a periodic train of clock pulse. We have on and off. This is off time, this is on time, this is off on. In this way it continues, and this time, one complete on and off time, is named as period T, and this is T on time, T on, and off T off time. So we know a term, we learned it from our electronic codes, uh, that is the duty cycle. Generally clock pulse has 50% duty cycle. What is duty cycle? Duty cycle is nothing but T on over big T, that is T on over period. The latches with control input are synchronized by giving clock pulse signal in the control input side. Now if we zoom a portion of this clock pulse train, you can see this is the zoom view of that portion. There are edges in both sides. We have edge in the left side and in the right side. When clock pulse goes from 0 to 1 signal, this edge is named as positive edge. When clock pulse goes from 0 to 1, this edge is named as positive edge. When clock pulse goes from 1 to 0, this portion is named as negative edge. Now sometimes we design our flip-flop that will change the output when the clock pulse value is 1. Then this type of flip-flop is called level triggered flip-flop. Sometimes we design our flip-flop when clock pulse goes from 0 to 1. During this transition period, whatever the value of S and R, for example, it will change the output. That type of flip-flop is named as positive edge triggered flip-flop. Whenever we design our flip-flop that will change its state when clock pulse goes from 1 to 0, that type of uh, flip-flop is named as negative edge triggered flip-flop. The detailed explanation will be given in the next slides. Here we can see uh, a typical Sr latch that is controlled by clock pulse. This is controlled by clock pulse. As I told you earlier, this uh, latch can be controlled by pulse transition, that means edge triggering. So we must have a pulse transition detector here. That means when clock pulse goes from 0 to 1 and 1 to 0, this transition detector will detect that change. I'll give you a description on pulse transition detector, a typical pulse transition detector. There are several methods of designing this pulse transition detector. Let's see how can we design a typical one. This is a typical logic diagram of pulse transition detector. This logic diagram or this circuit will be used to detect the positive edge transition. In principle, if we see the operation of the circuit, we know if we give an input in this format, suppose the input is 1 here, so and then that will give me 0 here and 1 here, and the output will be 0. And if I give 0 here, that will give us 1 here and 0 here, and output will be 0 over time. This is the case we see, but it's not always like that. Let's see the operation for a clock pulse. We know whenever we pass a signal through any gate, any logic gate, what happens? It takes some time to respond. Suppose a clock pulse is given here. In the output side of this NOT gate, we'll get the inverted output from here. From here to here, we'll get inverted output. However, even though it's a very small amount of time, but it will take or it will have some time delay while going from here to here because of this uh, logic gate. And in this side, the signal is connected directly. This signal is connected directly to the another input of the AND gate. So if you see this, the input here remains as we have here, and there will be no time delay because it's connected directly. So if we see very closely, there is a time delay in between these two signals. And in this time delay, you can see for this small amount of time, the signal is 1, and for this small amount of time, the signal is 1. And this both 1 will give us in the output side 1 for a small amount of time. So we'll get a glitch like this whenever clock pulse goes from 0 to 1. It will happen only clock pulse goes only when clock pulse goes from 0 to 1. It will but in this period both are 0, so the output will be 0. So whenever the clock pulse will go from 0 to 1 again, there will be another glitch, small glitch, so that we can see. So if we give this type of clock pulse signal, in this clock pulse signal in this input, in the output side we'll get this uh, edge detector output. That means in the output side we'll get when this type of signal, when clock pulse goes from 0 to 1, we'll get a glitch. When clock pulse goes from 0 to 1, we'll get a glitch. In this way, we can detect the positive edge triggering. This is a typical logic diagram which will detect the positive edge transition. There are other methods as well. We can design this type of circuit using some active and passive element. However, is it possible for you to design a logic diagram or circuit diagram which will detect the negative edge transition? It's a home task. You may try. Finally, You can say this is Sr Latch uh, that is connected with a control input, and that control input is supplied by a clock pulse. So combinedly, this portion is named as Sr flip-flop. Here you can see the graphical symbol for Sr flip-flop. We have S input here, R input, and the output is in the right side. There is one extra input, that is clock pulse input. This triangular shaped notch represents that the symbol we see here, the Sr flip-flop that is presented here, this is age-triggered flip-flop. If the flip-flop is level triggered, then we do not need to give this triangular shape. Moreover, this represents positive age-triggered flip-flop. If you want to represent a symbol that will represent the negative age-triggered flip-flop, just place a bubble at the clock pulse input. Let me show you another figure. Here we can see the graphical symbol of two SR flip-flop. One in the left side, you can see we have clock pulse input, and this is positive age triggered. In the right side, we have clock pulse input, but that input is having a bubble, which means it's age triggered flip-flop, but it is negative age triggered flip-flop. So by seeing the symbol of SR flip-flop, we can understand whether it is age triggered or level triggered, whether it is positive edge triggered or negative edge triggered. Let's draw the timeline diagram for two different flip-flop. You can see we have two symbol of two different flip-flop. One is edge triggered flip-flop. And there is a triangular notch, and another is level triggered flip-flop. The output for edge triggered flip-flop is Q1. The output for edge level triggered flip-flop is Q2. So Q1 will be drawn here and Q2 will be drawn here. As the first one is edge triggered flip-flop, so for clock pulse, and it's positive edge triggered flip-flop because there is no bubble. So let's draw the line for positive edge triggering. We see we have positive edge here, positive edge here, positive edge here. That means positive edge transition occurs here. So whenever clock pulse goes from 0 to 1, during this transition period, it will check the value of S and R, and output will be changed accordingly. Let's assume that initial value of Q1 is 0. At the very initial moment, clock pulse is 0, so we do not care about S and R value. The Q1 output will continue the previous value. Fine. When first transition occurs, that means this transition, it goes from 0 to 1. The value of S is 0, the value of R is 0, it will hold the previous value. Now, even though S becomes 1 here when clock pulse is having 1 here, but it doesn't matter, the output will not be changed when the clock pulse is 1, because this flip-flop detects only the edge triggering. That means when clock pulse goes from 0 to 1, at that moment the value of S and value of R will change the output value of Q1. So it, as though we have 1 here, we do not care about the inputs because there is it's not changing the state. Clock pulse is not changing its state, so it will continue the previous value. In the next transition, when clock pulse goes from 0 to 1, in this transition, let's check the input S equal to 0, R equal to 0. So again it will hold the previous data, and 0 will continue. Now again you can see from here the value of clock pulse is 1, S equal to 0, R equal to 1, but the circuit, the flip-flop will not go for reset condition, because even though clock pulse is 1, but this flip-flop is age triggered flip-flop, it will detect the positive edge of clock pulse. At that moment, the value of S and the value of R will detect the output pattern. So again, next transition occurs here when clock pulse goes from 0 to 1. We see again S equal to 0, R equal to 0, so it will hold the 0 0 will hold the previous data. We know. In this way, even though there are a lot of things, but there is no there are a lot of changes in S and R, but as there is no transition, we do not care about this input, it will hold the previous data. In the next transition, when it occurs, again we see this is 0 and 0. This 0 0 will hold the previous data. Now next transition, this is the next transition. We can see the value of S is 1 and value of R equal to 0. At this transition period, or during this transition period, the value of S equal to 1 and R equal to 0. S equal to 1 means it's set condition. So the output will go from 0 to 1 condition. The output will go for set condition. So this is the output diagram for first flip-flop Q1 output. Now let's draw the same output line for Q2, which is level triggered. What does level trigger mean? Level trigger means whenever clock pulse is 1, or as long as clock pulse is 1 during this transition, during this period, if there is any change, in S or R, the circuit or the flip-flop will act accordingly. So this clock pulse is 0 here. We do not care about this input. This input will hold the previous data. Fine. From from this transition to this point, clock pulse equal to 1, S equal to 0, R equal to 0, it will hold the previous data. Fine. Here, clock pulse equal to 1, clock pulse equal, let's draw the line, clock pulse equal to 1, S equal to 1, R equal to 0. As long as clock pulse equal to 1, we cannot ignore the value of S and R. S equal to 1 and R equal to 0. What will it return? It will return the set output. So at this moment, the output will go from Q2 output will go from 0 to 1, set output. Again, here clock pulse equal to 0, we do not care about this input, these inputs, it will hold the previous value. Okay, fine. Now, in this line, clock pulse goes from 0 to 1. That means clock pulse is 1 to this value. Let's draw the output for this portion. Clock pulse equal to 1, S equal to 0, R equal to 0. Whenever we have clock pulse equal to 1, it will see the values of S and R. S and R equal to both equals 0. It will return hold the previous fine. From here to here, clock pulse equal to 1, S equal to 0, R equal to 1. What does it mean? R equal to 1, it will reset the circuit. Clock pulse equal to 1, S equal to 0, R equal to 1, the circuit will go, or the output will go for reset condition. Fine. In this period, as clock pulse equal to 0, we do not care about this input, the output will hold the previous data. Again, let's draw this line, another line to make our idea clear. For this portion, clock pulse equal to 1, S equal to 0, R equal to 0, it will hold the previous up to this much. For this small amount of portion, clock pulse 1, S equal to 1, R equal to 0. So circuit will go for set condition, set condition. Again, for the third small portion, clock pulse 1, it's 0, it's 0. So it will 0 0 will hold the previous. And again, for this portion, the clock pulse is 0, we do not care about this input, it will hold the previous value. Again, clock pulse equal to 1 here, clock pulse 1 here, S equal to 0, R equal to 0, it will hold the previous, 0 0 will hold the previous. Here clock pulse equal to 1, S equal to 1, R equal to 0, S equal to 1, R equal to 0. It will set the circuit. Here clock pulse 0, we do not care about in these inputs. It will hold the previous. It will keep the previous data in memory. Again, here we have clock pulse 1, S1, R0. The circuit will be set. So this is the timeline diagram for two different flip-flop. One is for edge triggered, another is for level triggered flip-flop. I hope all of you understood. Now I want all of you to practice this type of timeline diagram on your paper. That will clarify your idea. We are almost at the end of today's lecture. Before I finish, let me give you a brief idea on the operation of SR flip-flop. I am repeating the operation again and again so that you don't forget. We can see here the positive edge triggered flip-flop, triggered flip-flop. So whenever positive edge triggering occurs, that means clock pulse goes from 0 to 1. If S equal to 1, S equal to 1 means output will be set. So output will be set. If S equal to 0, R equal to 0, it will hold the previous data. That means it will keep the previous data in memory. When clock pulse again goes from 0 to 1, that means positive is triggering. If the value of R is 1, what does it mean? R equal to 1 means the circuit will go for reset condition. Reset condition means the output will be 0. Again, for 0 0 condition, it will hold the previous data. And for 1 1, the output is invalid, as I described earlier. And this is negative edge triggered flip-flop, as we can see bubble here. So this is negative edge triggered flip-flop. For negative edge triggered flip-flop, the operation is exactly same as previous, but the change will occur, or the state change will occur when clock pulse goes from 1 to 0 at the negative edge side. When clock pulse goes from 1 to 0, and this is symbolized by downward arrow sign. When clock pulse goes from 1 to 0, if S equal to 1, output will be set. If R equal to 1, output will be reset. If S equal to 0, R equal to 0, it will hold the previous. S equal to 0, R equal to 0, it will hold the previous. And for 1 1 input, the output is invalid as described earlier. I think you have very clear idea on SR flip-flop. In the next class, uh, hopefully, I will describe other type of uh, flip-flops like D flip-flop, T flip-flop, JK flip-flop. Feel free to contact me if you have questions.